one. Okay, welcome back, everyone. We're happy to have the chief organizer, Borys Kadets, will tell us about points on abelian and Jacobian varieties.
Okay, thank you. And maybe in my role as an organizer, I want to just remind everyone again that tomorrow, 5:15, there will be a talk, the extra talk by Anshul Advait. It's not on the schedule right now. It will hopefully appear on the web page. I just have one more talk in the evening tomorrow on Zoom. Okay, and so I'll be talking about groups of points and abelian and Jacobian varieties, and there'll be two kind of independent parts. So I'll start talking about abelian varieties and then specialize to Jacobian varieties. And I recognize this is not an algebraic geometry conference, so let me start by saying a few words about what abelian varieties are, and it will not be very important for a big part of my talk. Okay, so I have some A, an abelian variety. Okay, I propose you think about three things, whichever one is more convenient. So first of all, I can very easily give you a definition. It's an abelian group which also happens to be a projective variety. Okay. So this is a great definition, though it's kind of hard to come up with examples of these.
I mean, you're assuming compatibility, I think.
I am, yes. Okay. So yeah, it's sort of hard to come up with examples, but that doesn't matter too much, other than look at curves in dimension 1, but very explicit examples. Now, over complex numbers, you should have, well, it's projective, so it's compact. So you have like a compactly abelian Lie group. There aren't that many of these, so the group of points is just some power of c to the n modulo lattice. At least as far as the group structure goes, that tells you everything you want to know about the group of points. And then there's another story that's particularly relevant over finite fields. There is an explicit abelian varieties called Jacobians attached to curves. And these are analogs in function fields of class groups, of number fields. The same thing as class groups. Okay. And hopefully one of these analogies is some way of thinking about it, and so just choose one. Okay. So I will, in fact, talk about things over finite fields. So I'm going to fix from now on. Imagining that I fixed a prime power q. And then, well, if I take an abelian variety, I can look at the group of points of an abelian variety over a finite field. There's going to be a finite abelian group. And in fact, there are only finitely many abelian varieties of every given dimension. So the theory of abelian varieties itself is a group producing machine. Okay, I give you a dimension, and it outputs you a finite collection of abelian groups. And so whenever you have such an object, there are lots of natural questions to ask about it, like what groups actually appear or how they distribute. So I will think about the case when the dimension of A is very large. So I want to understand, so how do these look like? That's finite abelian groups.
You're a tough guy. Some of us let Q get large, but you're going to fix Q.
Yes, I'm going to fix Q. Okay, so the first thing that come to mind, if you know anything about geometry or finite fields, that there should be this thing called wave bounds. I'll tell you what they say. I want to know how many points there are. Ignore the group structure. The claim this is because you know very precisely what these numbers should be. So it's roughly q to the power of dimension. Okay. Q to the 1/2 plus 1 like dimension of A. Okay, so this is sort of an exponentially growing number. So I started thinking about abelian varieties over finite fields by looking at this inequality and saying the following, that, okay, it's a standard assumption that the wave bounds basically tell you how many points you have in your abelian varieties. But it's not quite correct. So observe.
So Q could be 2, for instance?
Yeah. Q could be 2, 3, or 4. And whenever Q is 2, 3, or 4, you have no lower bound. So you actually don't know that these grow at all. In fact, a group always has at least 1 point. So even for Q equals 4, the inequality is trivial. Okay. So the question is why is this happening and what can we do about it? So Q equals 2, 3, 4, no lower bound. Well, this is really happening for a good reason. So there's this very old theorem of Doring. Like this. That says that in the case of dimension 1, for elliptic curves, any integer in the interval is achieved for every q. Okay, so in particular, what I care about is that for q equals 2, 3, 4, there exists an elliptic curve, one-dimensional abelian variety with EF of q, a trivial group. Once you have one such thing, you can now propagate this, and it will mess up all your point counts. So one thing you can do is you can take just the power of this elliptic curve. Okay, this will also have 1 point, and will have arbitrarily high dimension. You can do something slightly more clever. You can take, there's a notion of isogeny between abelian varieties. So you can take power of an elliptic curve, and then you can mod out by a subgroup. Okay, you have to make sense of this because I said there's only 1 point, but you can actually mod out by certain subgroups, get new abelian varieties, and they will still have trivial groups of points. And of course, if you look at, these inequalities, what we care about is somehow normalized point counts. So point counts to the power 1 over dimension. And so if you raise e to the very high power and then multiply by some small abelian variety, that will also have bad point count. Okay, so if we want to have a nice answer, we need to change the question slightly. Theorem. A couple of years ago, stated somewhat informally. So for every q, give me q, there are certain practically computable numbers called little a of q and capital A of q, such that I have to normalize by dimension of A.
So if Q is bigger than 4,
Mm-hmm.
are you putting something different to there?
Yes. So it does not. So this is not a formal theorem, indeed. But the point is that you can produce something which looks like wave bound with improved constants.
So what is little a of q for 2? You can give it a number.
So what do you mean by practically computable? So you asked. So for example, a of c. Well, I can tell you what it is. So it's kind of practically computable where you run the program forever and it gives you better and better and better bounds.
Give some
But
of
yeah,
it.
so I can give you a further one. Okay. And there's a table you can actually computed for small values of q if you want.
But you're assuming that A is not somehow a product or something, right? Or you're not assuming anything?
Absolutely right. This is true. Okay, this is important for all but finitely many. One condition simple. So you throw out all of these isogeny decompositions, just take simple things, and then you can improve the bounds. Get rid of
For
that.
2, you have a reasonable constant? Because 2 is,
Let me say something about
What do you mean by forever fancy many? There are fancy many. The varieties of a
No, dimension.
No, the dimension growing.
infinity, there is-
Q is fixed, but dimension, yeah, dimension.
But the question is whether this is effective. You could tell me that they all occur up to dimension 1,000,000 or something, or
This is effective. There's a question of how do I describe the abelian variety for you, but definitely in terms of dimension, I can tell you what dimensions appear in. Okay, so I'm cheating a little bit. So for 2, it doesn't do it.
Sharp. Your theorem is sharp. Must be smaller.
Well, here they're practically it's a little. Okay, the way I phrase it is a little difficult for me to answer. In a way, it's sharp by a non-trivial theorem of Alex Smith. I'll talk about it after this talk. All right. So for 2, there is a whole different story over F2. So A of 2 necessarily is 1. And that's because over F2, you do have infinitely many simple abelian varieties with 1 point. There's a beautiful story that they were discovered by Robinson. And then, so Madan and Sat.
What name Robinson is that?
Hmm?
What's the initial for Robinson?
RM, I think.
Not Julia.
But
It's not Julia Robinson.
it's not Julian. No. Someone.
No, because that's the film I'll quote.
Okay, so these people also give an explicit list of all A over F2 with F up to 1, and I mean they're actually infinitely many. You can't really improve the bound. So maybe why I want to talk about abelian varieties is to tell you that there is this abelian variety is one of the most studied objects in number theory, and if you ask someone, like there's a general expectation that there's a question about abelian varieties, it's either well known or completely impossible. And I want to convince you this is not true. So there's been kind of a revival of studying abelian varieties over finite fields in the last couple of years with lots of new interesting results, which I'll also mention a couple of problems I think are still haven't been resolved fully. Okay, so I'm going to call this A-F-2 revival. Okay. So about this A-F2. So F2 is the most interesting case, but I have little to say about it. But Karan-Kedlaya has been proving many results about what happens for abelian varieties over F2. In particular, a couple of months ago, he proved that in, for example, every dimension, there exists A over F2 with AF of 2 with exactly 2 points. Okay. Well, let me say simple. I'm just twisting these.
So in your work, are you just using 100 Tate or do you use more?
For this, just 100 Tate. And, okay, he proves more. So the expectation is that for every m...
He's also only using it.
He is only... Yes. Well, 100 Tate with some decorations. Like from 100 Tate, you can also put other adjectives like ordinary. But it's tricky. So the expectation is that in every dimension, whenever M you would have in also very large dimensions if you invariate with those point counts, you probably actually have many. That's the goal, and there are sort of various results that there are actually a sequence of papers trying to do better and better. Hopefully, hopefully, ask me in a couple of years, we'll have a better theorems about abelian varieties over F2. But, right now, that's the most mysterious part. Let me mention two more theorems. There's the theorem T2 von Bommel, Costa, V, Funen, probably. All the names I have. Okay. This is a preprint from 21. The Q is fixed, and then the way that they prove many results, the way they phrase it usually is that every large integer is size of A over Q. Thanks.
Change it.
Every large integer is point count for some A. Okay, for simple ordinary. Okay, you can put multiple adjectives. Ask me about them. Doesn't matter. Many adjectives here.
Is being large and effective.
Yes, for a given Q. Yes, perfect. What they actually prove though is something I can draw. So there is this Weil interval in which are these normalized point counts. And okay, I'll say Q is not too full in drawing. That what I prove is that you can sort of move by a constant amount inside the interval to improve the Weil bounds. Okay. What they prove is that if there's another constant amount, a very tiny amount, you can move in such that on this interval everything is achieved. This is the actual picture. So also you can't improve Weil bounds too much. So this is really a game for small values of Q. Okay, I haven't said anything about groups. Let me just.
You're missing like the dimension of A in your
Dimension is 2.
Oh, no, I'm thinking about the normalized point counts. So I'm taking the number A of Q to the power 1 over dimension of A.
If you were to put the, can you draw on the circle of where the Frobenius eigenvalues are, you showing where the location of the eigenvalues are basically?
Well, it's
not,
essentially the location of individual, sort of about how the way they distribute is biased, I guess, a little bit. Okay. Let me just say that I'm saying here all the theorems about point counts for now, but you can prove things about group structures. To prove those, you need more than just this Honda Tate, what I'll talk about next. Just want to mention this as part of this revival. So there's a theorem of Mastelia and Springer. From a year ago. Okay, so if you Q is small, 2, 3, or 5, is fixed, then every finite group, finite abelian group, is a, in fact, you can say for an ordinary A. they're cheating a little bit, so it's not for simple ones. What they prove is you get all cyclic. You get all cyclic groups and then take a look. Okay, now the question is, why am I talking about this here? So these all results about abelian varieties, and it's all nice. But the truth is, maybe, except for this, these are results about distributions of algebraic numbers. What I want to say maybe is how this is connected to, well, very explicit problems about polynomials. All right. So, okay, it works like this. I have an abelian variety over Q. There's a general thing that all varieties over Q are special. Okay, just the fact that they're defined over Q makes them special. Because every variety over a finite field gets an automorphism called the Frobenius morphism. And it's not just like it's a meaningful statement. It's not about characteristic P, it's about being defined over a finite field. It's true that automatically you get this extra object called the Frobenius endomorphism. Since this is a group, it's better not talk about automorphisms, but endomorphisms of A, which is a certain ring over Z. It's an abelian group. And when you have an element of such a ring, you can attach to it its minimal polynomial. Just a certain integer polynomial. So this is an abstract thing, and this is an abstract thing, and this is a concrete thing. So that's what matters. And so they proved in the 40s that these polynomials are in fact very special, that, okay, the PA are monic, and their roots are what's called QA numbers. I'll draw what it means, but okay, this is an analytic condition. They all lie in a circle of certain radius. Okay. There is a wonderful theorem due to Honda and Tate.
Bayes is also
Yes, no, I'm not. I will run out of adjectives if I try to. Oh, okay. Maybe black will be visible. Theorem, it's really two theorems. Okay. Correct name is Honda plus Tate. So this construction attaches to an abelian variety of polynomial. And if you think about it a little more, it gives a map from simple abelian varieties, okay, up to isogeny, to QA numbers, where, okay, this doesn't give you a number, it gives you a polynomial. So by number, I mean the root of this polynomial, and then my identification will be the Galois conjugacy. Roots of these polynomials. Okay, so basically, abelian variety is the same thing as QA numbers. And so the theorem is that this is a bijection. So the fact that it's an injection was proved by Tate, an example of Tate's conjecture of finite fields. The fact that it's a surjection is proved by Honda, in a way, kind of vastly generalizing this work of Dorian that you mentioned about elliptic curves, right? Reducing some special abelian varieties from characteristic 0 to characteristic p. Okay. The point is, though, that everything I mentioned about point counts is a question about polynomials, a question about roots of polynomials, monic integer polynomials. Maybe let me say here that if A corresponds to a number gamma, then my normalized point count, normalized, okay, temporarily like this, 1 or twice dimension of A, the same thing as a norm, field theoretic norm, 1 minus gamma to the power 1 over degree of gamma. Now I can draw what a QA number is. So we have a circle whose radius is the square root of Q. Row number 1 here. And then a QA number means it's in we give a polynomials, integer coefficients, all roots have to be on the circle. So what you want to understand is the product of like 1 minus the root. And of course the weight bounds are just saying either all roots here or all roots there. And you should expect that these distribute somehow nicely to average out, to give you better. Okay. So I will not think about it as happening in the circle. I'll translate it to a real interval. Sort of how you go from roots of unity to trigonometric functions.
How complicated are these algebraic numbers? I mean, on the unit circle, the number and all its conjugates are on the unit circle.
Yeah, this is square root Q. They're very complicated.
Yeah, so I
They're
mean,
not roots of unity.
it's not. You can't fit them into any nice family. Okay.
Yeah,
I mean,
that's why it's not the unit circle.
Yeah.
Makes it so difficult.
Okay, so I want to replace for the elementary gamma with 1 minus alpha times 1 minus alpha bar to make it a real number. This is also an algebraic integer. Sorry. This is going to be an algebraic integer. Okay, and so all of its conjugates are now going to be in the real segment because we'll multiply it by the conjugate. So now let's call this number alpha. So alpha is going to be totally real, so it means all conjugates are real. And the conjugates lie on some interval. Okay, it's our way interval. And we want to estimate the norm. So normalized way, we want to understand the geometric mean. Okay, so you have some interval and you want to understand how the geometric mean of a conjugate of an algebraic integer can look like. Those conjugates all lie on a segment. You can forget about abelian varieties, and even what these numbers specifically are doesn't matter too much. You want to understand the distributions of real algebraic integers on the segment.
I mean, your number is what? Is that a function of 1 or something? The actual number that you can.
Yes, but once I translate it this way, it's a norm.
Okay. It's a norm.
By the function, you mean the function of the real varieties? Or?
Yeah.
Okay, this is not
Possible.
quite. Okay, it's not quite the.
There's a factor there.
It's a factor inside that function, but I'm just saying. So my number is. It's a norm of 1 minus gamma. It's the value of the minimal polynomial gamma evaluated at 1. Okay. So now here's a little math break. We'll do some high school algebra. Okay. So this corresponds to the case q equals 4. So let's say we want to look at all algebraic integers which are from 1 to plus infinity. Okay, so all conjugates from 1 to plus infinity. So let's say alpha, so here's a claim. Say alpha is not equal to 1. Then I claim that the norm of alpha is at least 2 to the power degree alpha. So it jumps. The next normalized geometric mean has to be at 2 or larger. Okay. Proof. Well, let me say alpha is 1 plus beta. Okay. This is still an algebraic integer. So I have my norm 1 plus beta 1 up to there's the most important inequality in number theory, which is that an integer which is not 0 is at least 1. So despite the fact that some of these numbers are quite small, this has to be under the square root. This is an integer, so this at least to do the n. So this is kind of a trivial inequality. But you can improve just on this idea to quite a large extent. So the first thing you can observe is that I can move a little bit to the left of 1 and nothing changes. So if I move a little bit to the left of 1, so let's say from like 0.9 to 1, so how can I rewrite this expression? What I used here is the inequality that, well, x is larger than 2 times x minus 1 to the power 1 half. And this has to stay true to the left of 1 a little bit, because right side is 0 to 1. Right? I can repeat the same argument by considering, in other words, I can consider this function x over x minus 1 to the power 1 half. And then I have this argument where I take the product of values of this function and my conjugates, and I see that, well, the minimum of this function is 2, so f of x is 2. Gives me the improved inequality, even if I step a little bit to the left of 1. But now I can change my function and step quite far to the left of 1. So to make this argument work, like this was very ad hoc. And if I write anything here, so if I can consider any function of the form x over some integral polynomials to some powers, okay. So if I understand this number, which is the max over all choices of pi and all choices of numbers alpha I, alpha I bigger than 0, of the minimum of this function. So if C is this number, then with finitely many exceptions, you get that the norm of alpha is at least C to the power degree of alpha. Right? By the same argument. Now you can ask a computer to find a good function for you. Okay, so you can choose lots of polynomials and solve a linear optimization problem. Taking logs, specialize into a mesh, it's now a linear programming problem to find the good values for C. So for example, to get this inequality for q equals 3, you basically have to step somewhere to 1/2 here and still get a good inequality, and it still grows exponentially. The function is not very pretty. That's what you do.
Do you actually use the computer to get these?
Yes. Okay. Now maybe I can advertise the next talk. But this looks very ad hoc. But Alex Smith's proof, I guess this was published this year, that so these are the only abstractions. While this looks like kind of an ad hoc restriction on the numbers, like this is all you have to compute to figure out what the growth actually is.
Was there any structure to the polynomials you found?
There's a little bit of structure. So you see, this inequality has exceptions. The exceptions are polynomials in denominator. So first I find all the abelian varieties that I want to throw out. And then I have to put them in the denominator. And then I just throw in whatever comes to mind to get like a big bag of polynomials and put it into a computer. Try to optimize. Okay, so this is what I had to say about general abelian varieties. And maybe for the rest of my talk, I want to say a few words about
So if you
Jacobi
say explicitly polarize something like that, which puts some structure on the zeros, Jacobian
Mhm.
is not as much change. I mean, Jacobians are now a lot of change, but
Mhm.
you put like with abelian variety, then you're going to have some symplectic structure to the roots there. If you put some adjectives,
I wouldn't expect there to be any change. Really. Like adjectives are typically satisfied. Ordinary.
By these are the only obstructions. It seems that seminal ruling is about dynamics. Does it mean that there is some equidistribution of such QB numbers in the set?
Well, there is a description of the set of limiting norms.
limiting measures.
Limiting certain measures, yes.
Yeah.
I want to say a few words about Jacobians. Maybe let me say there are some reasons to care about Jacobians more than to care. There are more reasons to care about Jacobians than to care about general Abelian varieties, I think. So Jacobians are Abelian varieties which are attached to curves. First of all, they're correspondingly explicitly described. Have x, which is some curve over a finite field. Given by an equation. I can look at this function field of this curve, all the rational functions in x. And, okay, well, I think starting somewhere maybe in Artin's thesis, that this is kind of like number fields, okay? So it's interesting to study arithmetic over these fields. Now, Jacobians are something like class groups for these objects. Let me describe this. So first of all, to describe class groups, I need to tell you what are the ideals and the prime ideals, and then tell you what are the principal ideals. So the ideals in this language is this set. You take, this is the prime ideals, you take all points on your curve, Q bar, then you mod out by the Frobenius action. So you take the orbits of Frobenius. So on the affine line, these are irreducible polynomials. They're kind of like prime numbers. So these are your analogs of primes. And if you want to define sort of all ideals, you take formal linear combination of primes. They're called divisors. So formal Z linear combinations of more or less points. Okay, and if I have a rational function in my x, I get a divisor. I look at zeros and poles. I have x, I get the divisor of f. Zeros minus poles, let's correct with these. So to get the class group, you mod out the group of divisors by the group of principal divisors. So it's not quite the correct analog, so I'll put a half in it. So the class group of x is divisors modulo the principal divisors. It's also called the Picard group. The reason it's not quite correct is because curves are compact, and so you have as many zeros as you have poles, which means that you have a degree map to the integers. So these class groups, the way they're defined, they're infinite. they're infinite for a single reason. There is this degree. So you can define the kernel of the degree. It's called big node of x. Okay, and so this is a finite abelian group. This finite abelian group, it's sort of like a class group in algebraic sense. Analytically, it does not behave like a class group. Okay, so these are quite big. The reason they're big is because they are secretly groups of points in certain abelian varieties. So really, there's a certain abelian variety A called the Jacobian, such that AF of Q is this. Okay. Right. Right. Let me say enough to state a theorem. Now, in sort of number fields, there are interesting problems, like a class number 1 problem. It's interesting to understand what happens, like when are these groups small? It does not become, it's not a very interesting problem over function fields, because these are very big. But there is a good analog. In fact, this is what Artin discovered. So Artin was looking at analogs of the theory of imaginary quadratic fields in their class groups, like a classical class number 1 problem. And he understood that they get a bunch of two torsion. So what he was interested in is, okay, let's just ignore the two torsion. Is the remaining class group trivial or not? How does that grow? So the interesting invariant is the exponent of the group. Okay? To measure how big it is the exponent of the, it's called the Jacobian. Yeah, the Jacobian. And now this group grows exponentially, but the amount of torsion in a torus also grows exponentially in dimension. So it is conceivable that these are just bounded. There's no, so wave bounds tell you nothing about how big this number is. The wave bounds
But before you look at this, if you just look at the bounds for Jacobians as abelian varieties in the previous discussion.
Mm-hmm.
Don't you get improvement? I mean, the
Yes.
spectrum, the zeros rigidify by theorem of Ladut and Schwarzman, right?
Yes, and
So it's rigidity, and that would force much better behavior.
yes, I can tell. So I know two arguments. There's the polynomial argument about Ladut and Schwarzman. There is what I think is better, and what goes into the theorem about the state is purely geometric calculations of what these numbers are. So I can
Can they give
say
different things or not?
I don't know how to I don't know how to deduce what I can say geometrically from Ladut and Schwarzman. But I don't know. I mean, one of the issues is that these aren't simple.
Yeah. Let's just.
Okay, so what you want to understand is it's possible that these are just bound. State two theorems. So these are both joint work with Daniel Kelleher from this year. The exponent of the Jacobian, at least, okay, so it does grow. Right? So roughly, these are explicit inequalities that are easier to write kind of informally. Gonality of x, or genus over the gonality of x, by some log. And we can write explicit inequalities, so not optimized, but here's 1 e to the 1/2 or log q times g naught. Something. But it's explicit. So the exponents are actually unbounded. Okay, they do grow with genus. So genus is a dimension. G is the dimension. Look, okay, it calls the gonality of x. Doesn't matter, like this inequality. You don't know what gonality is. This is the inequality.
It's what I defined in my lecture. It's the least degree cover of the curve. The hyperelliptic is gonality 2.
So, better, you can say what happens in the relative case. So you can start with a separable morphism. It's a covering of curves. And then there are relative class groups. So you can look at the exponent of the class group of x1 modulo the class group of x2. And so these are also bounded. Won't write explicit now, but it's like the g1 over 1/2 times log times degree phi. Another inequality. So this is okay. The reason I wrote these inequalities, what I want to end with, is to advertise a problem. So for so the set exponents of class groups, I think, are a good replacement for sizes of class groups. So problems about how big the class group is, a more interesting question, how big the exponent is of the function. Questions of how big the relative class groups are, number fields, should be replaced by this. Now if you stare at these inequalities long enough, you can realize they don't actually tell you that these things are growing. So
If the curve has got big gonality, then you do better.
let me state the problem and then I'll just point to the correct inequality. Okay. The open problem is, is the set of phi x1, x2, for which E is bounded to a given number, exponent equals E, well, finite. So I don't know. Okay, so you can do this, Lia did this for equals 1, where, also this year, it equals 1. And exponent 1 is the same thing as size 1. It's a completely different kind of question. What is interesting that those inequalities tell you that there is a very thin range of parameters when this can occur. So this is supposed to occur when so G2 and the degree of the map, okay, roughly, are all just G1 to the power 1/2, which means this is an unramified covering. Okay, so it's have genus G curve and then a degree G unramified covering on that curve. So this is geometrically a very special range of parameters. So it kind of suggests that it's possible the answer is no. There are some special examples here. Okay, so you're asking about gonality here?
I mixed up the gonality big is bad.
Well, it's very big. It's also good.
Yeah, but the gonality is small, it's also good.
Yes.
Yeah.
Okay, let me stop here.